for the continuous user authentication. They usually need to analyze some data when you type in a keyword, for example, the key press duration, this type of information, to extract a unique pattern. Also, they can use some mouse dynamic objects and mouse. But this type of research, the research only works when the user operates a mouse or a keyboard. So it's largely limits its usage in practice. And recently, a couple of studies shows the initial access of using Wi-Fi signals for the user authentication. However, currently all the Wi-Fi-based approaches can only identify the working people. They can capture the unique working gate pattern from the Wi-Fi signals and then do the further user identification. And they also require the users to work through well-designed paths, or they have the Wi-Fi transmitter receiver placed close to each other, which is not that practical in many real-time scenarios. The different from existing solutions, our work is based on two key observations. The first, we found that the physiological characteristics can be used to distinguish different people. For example, the different body shapes or different weight, different height. And this is very straightforward. For example, sometimes we can even use our eyes to distinguish different people far away only from their body shape. And also, the second one, we found that the behavior characteristics embedded in the daily activity the people perform can also be used to distinguish different people. For example, because even people perform exactly the same activity, they can perform that activity in different ways. And this observation has been validated in an existing work published in 2015 UBCOM. They asked the people to do a series of activities in a home. And also they asked the people to wear a smartwatch when they perform such activities. The authors can only rely on the motion sensor readings from the smartwatch to distinguish different people, because they found that even the same activity, different people may have different ways to perform that activity. So in this work, actually we want to use both physiological characteristics and the behavior characteristics to do the user authentication. So this is a question: can we utilize such unique characteristics embedded in daily activities to do the user identification using Wi-Fi signals? That is what we want to do. So the basic idea is that our work is want to use prevalent Wi-Fi signals to extract such unique physiological and behavior properties embedded in the people's daily activities to do the authentication. And this daily activities, including working activity, that you just work from one position to the other position, and also is to use the stationary activities. That's, for example, the brushing teeth or open the door or fetching documents. That all is stationary activity, which involves small-scale body movements. And also, we want to utilize many smart devices, such as the smart television, smart printer, and we use the Wi-Fi signal in between these devices to well capture such environmental changes associated with the human body movements. And then we want to extract some features from these Wi-Fi signals, and after that, we want to do the further user authentication. So to be more specifically, we want to use both CSI amplitude and relative phase. This is CSI channel state information. We can extract this value from the Wi-Fi signals. And we show the extracted CSI amplitude for when two users working along with the same trajectory or opening a cabinet. So this is two figures show this CSI amplitude. And different color represent different users. And for each color, we have two curves. That means each participant is asked to perform 3 rounds of activities. So we can see for the working activity, that's the left figure. It's okay. We can use this CSI amplitude is distinguishable. We can use this information to distinguish different users. But for the stationary activities, such as opening a cabinet, such uniqueness is not that significant compared to the working activities, because this stationary activity only involves the small-scale body movements. So to cope with this challenge, we propose to use relative phase to capture such uniqueness. As illustrated in this figure, in this figure, we have one transmitting antenna and two receiving antennas, so that we can have two transmission paths. And because of the reflection from the human body, we have a distance difference between these two transmission paths. And this distance difference, delta D, would be vary with the body movements, thereby resulting in the relative phase shift. So we also show the formula of this relative phase, and we can see the lambda is the wavelength of the signal, and the delta D is the distance difference between the two transmission paths. We can see, given the centimeter level of the wavelength lambda, the relative phase is capable of capturing very tiny body movements of the user. So that we want to use this relative phase to capture such body movements, even the user is performing the stationary activities. And we show the extracted channel states information relative phase when the user is working with the same trajectory or is opening a cabinet. We can see now the relative phase looks much better compared to the CSI amplitude. All these different color curves can be distinguished, and we have a very good pattern. So in this project, we want to use both CSI amplitude and the relative phase to capture both working activities and stationary activities. In our system overview, our system first takes us input a time series of CSI measurements, and then we extract both CSI amplitude and CSI relative phase. And after that, the data calibration and the subcarrier selection is deployed to eliminate the environmental noises and interference. And after that, we calculate the moving invariance and this short-time energy to detect the useful segment of the daily activities, including the working activity and the stationary activity. And after that, for each individual segment, we extract features from both time domain and frequency domain to capture the physiological and the behavior features from the activities. And after that, we will include all the features into the deep learning machine model. That's excuse me. And the model here consists of 3 layers. You can see that we use a 3-layer deep neural network to train a model. And in the first layer is activity separation. That is, we can use this layer to closely distinguish whether the activity is a working activity or stationary activity. And in the second layer, activity recognition, we can show the activity details, that we can show the trajectory of your working or the type of the stationary activities. And in the third layer, that is the user authentication. We want to know who performed these activities. So this is a final step. We want to use this step to do the user authentication. And also we have an SVM-based spoofer detection to detect the potential spoofer. And basically the output of this system can have 2 steps, can have 2 categories. The first is activity recognition. We can know what type of activity you perform. And also we have a user authentication, we can know who performed this activity. So in the data calibration and subcarrier selection, we first correct the phase error using the unwrapping by adding 2 pi or minus 2 pi. We can see that for the this figure shows the raw relative phase of the 3 subcarriers. It contains lots of discontinuities. And after unwrapping, we can see we have already removed all of these errors. And also we use a bandpass filter to remove the high frequency and the low frequency noises. And in the subcarrier selection, we observe that all the CSI measurements on the neighboring subcarriers are highly correlated. But such correlation will be destroyed by the heavy noises. So we design a score based on covariance. We calculate this score for each subcarrier. And then we, based on this score, to determine the noises received in subcarriers. For example, there are 2 calculated scores. We have the first subcarriers, we can see that this red curve is subcarrier 7. It has the lowest score, and also it contains lots of noise because, for example, for that figure actually it's an empty room, but the relative phase of this subcarrier 7 so varies a lot. So this is the policy with the noises, so that we can use this score to determine which subcarrier is sensitive to the noises. And finally, we use this metric to select the 20 subcarriers with the highest scores. And in the activity segmentation, we first calculate the moving variance on the CSI amplitude, and also we calculate the short time energy. For example, in this figure actually shows 2 rounds of activities. And when we observe that the short time energy exhibits the much higher value compared to the rest of the data. So that we can use the dynamic threshold to distinguish which part of the data contains the activity and do the segmentation. And the following 2 figures are the corresponding the CSI amplitude and the CSI relative phase, so that we can do this segment. After segmentation, we'll extract feature from each individual segment. And to achieve the finer feature granularity, we first partition each CSI segment into L chunks. And for example, this chunk memory is 20, and with the equal length. And also we extract 6 time domain features from each trunk and on the CSI amplitude and the relative phase. For example, in these 6 figures, we show the CSI time domain features: maximum value, minimum value, mean value, skewness, or process, or the standard deviation. The x-axis is 20 chunks, the index of the chunks, and the y-axis is corresponding feature values. And we can see different users may have the different features, so that we want to use this CSI time domain features to distinguish different users. Also, besides the time domain feature, we also extract the frequency domain features, because the frequency domain features can be used to indicate the speed of Wi-Fi path length changes associated with the user's activities. Particularly, we extract the 3 features in each time window that includes spectral magnitude, percentile frequency component, and the spectrogram difference. Once we got all the feature set, we'll include all the feature set into the deep learning model. Basically, we have 3-layer deep neural network. And in the first layer is activity separation, and we can distinguish whether activity is working or stationary activity. And the second layer, actually, this model is like a theoretical model. So basically, we do the recognition one step by one step. And the second layer is deeper than the last layer. So the second layer is for the working activity, we can distinguish the trajectory the user walks, and for the stationary activity, we can distinguish the type of the activity the user performs. And the last layer, and the layer 3, we can distinguish, we can recognize who performed this activity. Also, we have SVM-based spoofer detection. So for each user will build a SVM model. We'll set a threshold to distinguish whether this detected user is a 50-minute user or potential spoofer. Yeah, for the spoofer detection, we use a one-class SVM, and actually we use the abstraction derived from the DME model and to build this SVM model. And we use the Gaussian kernel to train the model, and we set the SVM distance at the threshold to distinguish the user is a legitimate user or a spoofer. And in our experiments, we use 2 laptops to emulate the IoT devices. And these 2 laptops are equipped with the Intel 5300 NIC. And also we conduct our experiments in 2 typical rooms. One is the university office, and the other one is the apartment. And also for the office, we involve 11 subjects. And for the home environment, we involve 5 subjects. Actually, this is a very reasonable number is like the number of the family members in a big family. So 5 members in a home, and for the office environment, we have 11 employees. So we chose these 2 numbers to conduct our experiments. And also for the daily activities, we involved 8 working activities in a room, and also we involved 8 types of stationary activities. And we asked each participant perform the 30 rounds of activities, 30 rounds per activities. So, and these typical activities involve some like typing on keyboard, light switches, open the cabinet or function documents, open the microwave door, open the door. Yeah, all this activity can very common in the home or office environment. And we can see for the user authentication, we can achieve the average accuracy is about 91% for the office environment and about 92% for the terminal environment. And for the office environment, 7 out of 11 users can achieve around 92% accuracy, and for the home environment, 4 out of 5 users achieve over 90% accuracy. Actually, this is very, we can achieve comparable to the accuracy that demonstrates we can accurately identify the users. And also we have spoofer detection with the SVM model. Through adjusting the threshold, you can see the x-axis in this figure is threshold for the spoofer detection. And the blue curve is the spoofer detection accuracy, and the right curve is the user identification accuracy. So through changing this threshold, we can get optimized accuracy for both spoofer detection and the user identification. So once we got optimized point, we can achieve about 90% accuracy for both spoofer detection and user identification. Also, our system, besides the user authentication, we also can do the activity recognition. So for the performance of activity recognition, it's slightly higher than the user authentication. We can achieve about 97% accuracy for the office environment and about 98% accuracy for the apartment environment, because this activity recognition is happening in the second layer of the deep learning model. So we can get comparable high accuracy for both stationary activity and working activity. So let's come to our work. Basically, in this work, we want to use Wi-Fi signals to extract both physiological and behavior features from human state activity. We want to use this information to, first we can distinguish what type of activity they perform, and second we can distinguish who performed this activity. And also we study both amplitude of the CSA and the relative phase of the CSA. We can show the relative phase shows slightly better than the amplitude, especially capturing the subsequent movement of the user. And we designed a 3-layer deep learning model to do both user authentication and activity recognition. And we performed extensive experiments involving 2 typical home environments and office environments, demonstrated effectiveness